So in the yesterday, we started our discussion on MOS transistor, and we discussed about the operation of MOS transistor. So different regions of operation. We talked about accumulation, depletion, inversion. So we'll go ahead today and discuss the next steps. We'll also talk about some equations, right? Um, so we derived means basically to recap the things. Um, so when you apply a positive gate voltage to the gates of a MOS transistor, so here I am taking example of an NMOS transistor. When you apply positive gate voltage, so there is an electric field. Um, so there is an electric field from gate to substrate. So this electric field repels the holes and expose this negatively charged acceptor ions, right? And since we have negatively charged acceptor ions here, so we have some potential, and we also figured out that that potential is positive, right? And if this is my x direction here, so also yesterday we derived this psi x from the surface of your transistors, that is the means oxide and silicon interface towards the body, towards the bulk. So this psi x is qna divided 2 epsilon, 2 epsilon, and wd minus x square. Wd is the depletion width, right? So here, if you plot psi x as a function of x, this is a quadratic equation. So at the surface, right, the surface potential is the surface potential. Sorry, it's already written. So the surface potential is qna divided by 2 epsilon wd square, right? So as you go on increasing the gate voltage, your depletion width will increase, as well as your surface potential increase, as well as your potential. And we discussed yesterday also the average potential in this region, right? So will increase, right? Since the potential in the p substrate is increasing, so your both the junctions, so your source to body junction and drain to body junction will be forward biased, and electrons will be injected from source to the body, the source to the body. And since we have an electric field which is from gate to substrate, so the electrons will be pulled up because there is electric field, and these electrons will be accumulated at the surface, right? And the channel will be formed, right? So if the electron concentration at some, I mean, if the electron concentration becomes equal to the whole concentration in the body, which is Na in this case, because the doping is Na, right? So that gate voltage will call the threshold voltage, and that condition will call the inversion condition, right? So inversion condition is nothing but when the number of electrons at the surface becomes equal to the number of holes in the body, right? So it's like I had n number of holes, but now I have n number of electrons. So if you look at the surface has inverted from hole majority region to electron majority region. So that's we call the inversion region. Okay, so this we know. So if I we'll start with the band diagram, because we'll go and write some equations. For that we need to have the band diagram, energy band diagram. So if I look in this direction here, right, from the gate to the body. So if I want to do the band diagram, if I draw plot the energy band diagram, so let's assume my length, right? A length is much higher than your oxide thickness, right? So this is nothing but a long channel MOS transistor, right? So because we will do all our analysis with long channel MOS transistor, and once we understand long channel MOS transistor, then we'll go to the short channel devices, right? Okay. So if I take a, means basically if I look from this region here, right, this region here, right? So when I plot the energy band diagram, I'll plot the energy band diagram in the silicon. So your ECX, right? So because I have a surface potential, I have a potential. So your EC, the conduction band will nothing but EC0. EC0 means when you're not applying any voltage, the bands will be flat. I'll show that. So your ECX will be EC0, which is nothing but I could better to write it at EC flat band. So EC in the flat band condition, and similarly I could write down. Oh, this was correct, right? Oh, yeah. So EC flat band minus Q times psi x, because this is how my conduction band will change. Since the conduction band is changing, your valence band will be changed also. So because EVX is nothing but ECX minus EG, right? Okay. So when I plot the energy band diagram, so um, if you look at here, um, so so basically in the MOS transistor I could plot energy band diagram looking at gate to the substrate. So this direction, this is my x direction, right? This direction, this is my x direction. Or I could plot also from source to drain. So this will be my y direction, right? So this will be my y direction, right? um, okay. uh, so let's start with the x direction band diagram. um, so here, okay, so let's talk about the flat band condition, right? So flat band condition, that means as I told you yesterday, we started with that your oxide is ideal, right? So these two conditions, your oxide is ideal, the gate dielectric is ideal. We have ideal gate dielectric. That means we do not have any charges there, and your the metal work function is equal to the semiconductor work functions, right? So the phi m is equal to phi s, right? So your metal work function is equal to semiconductor work function, right? So phi m equal to phi s, right? So if that is the case, right, in the flat band, if you're not applying any gate voltage, right, if not applying any gate voltage, so there is no charge, there is no potential, right? So bands are flat. So if you look at the silicon, you see the silicon, the bands are flat, and you have a metal, right? So since there is no current flowing, right, both the Fermi levels are aligned, right? So basically, you see, I mean, so um, your formulable. So if you see, um, so there is no current flowing, right? So there is no current flowing. So my formulable will be flat, right? There will be no change in the formulable since there is no current flowing, right? So basically there will be no current flowing in the x direction, right? Because x direction there is no current flow, because that we have a gate dielectric sitting here, insulator sitting in the path, so there will be no current flowing. So whenever you want to plot the band diagram in the x direction, your formulable will always be flat, right? Okay, so so your phi m equal to phi s, so your both the formulables are aligned, right? And you have your conduction band, right? So you have your conduction band and valence band, right? Right. So right. And this is the metal, and here in the between we have silicon dioxide, right? Which is semiconductor. The semiconductor, because this is, sorry, silicon dioxide is insulator, so this has a very high band gap, and these 2 points is the band offset, right? So this is the conduction band offset, right? Uh, right, let's say conduction band offset, right? And this is the valence band offset, right? This is the uh, valence band offset, right? So these things you could get from the on the internet. This what is the conduction band offset? The silicon dioxide interface is very well studied, and we know what is the conduction band offset and valence band offset. Okay, so here you see your psi x, the surface potential is zero because there is no band bending. So the surface potential is your potential in the silicon is zero, right? And your psi s, your surface potential is also zero, right? But when I apply positive gate voltage, right? So I'll apply positive gate voltage, right? If I apply positive gate voltage, there will be charge in the silicon. If you look at the silicon, there will be some charge, right? There will be depletion, there will be some charge, and we'll have the surface potential. We will have the potential psi x, right? So uh, as I told you, right? So your psi x is positive, right? So when you're applying positive voltage, your psi is positive, your potential is positive, right? So I told you why it will be positive, right? So if you look at right, if this is my gate, I'm applying gate voltage here, right? Let's say this is my oxide, and then I have my depletion charges here, right? And this is grounded, right? So your gate voltage is positive and your body is grounded. So and I'll have some potential here because this is where I have charges, right? Right. And basically this potential, which is nothing but psi, I am talking about psi here, right? And psi varies from this end to this end, so this is psi x, right? So this psi will be positive because the voltage will be somewhere between Vg and, because you have to always follow the Kirchhoff's voltage law, right? So if you're applying some gate voltage, so there will be some drop in the silicon, right? And that is positive. That will be positive, right? So this is psi. Um, so since the psi is positive here, so your conduction band will be conduction band in the flat band condition minus q times psi x, and your valence band is Ecx minus Eg. So here, if you want, so then you could plot them. So right, so there will be some band bending, right, at the surface, right? There will be some band bending at the surface, and similarly there will be band bending in the conduction band and valence band. And this, right, this is your WD, right? Because at the edge of depletion width, your potential will be zero. The moment the potential will be zero, your your conduction band will be the conduction band in the flat band conditions, right? Um, right, and this is your psi x, and this potential here, right? So this is this part is your q psi s, right? So this is the surface potential, right? Surface potential q psi s. So this portion here, or if you could plot also here, this is your q times psi s, right? Right. So this is the surface potential, right? And as it and also if you look at the gate, since there is an electric field, there is an electric field from gate to the substrate. So there will also be a voltage drop in the oxide, right? And as you discussed yesterday, this is q times Vox, right? So if you look the your q times Vg, or your q times Vg, if you know, if you go from the gate towards the body, so your q times Vg will be q times Vox plus q times psi s, right? So your Vg is nothing but your Vox plus psi s, right? And the psi s is the potential drop in your silicon. This is the total potential drop in the silicon, right? If there is no gate voltage, there is no charge, your psi s will be zero. Your, because there will be no electric field, your Vox will also be zero, right? And Vg, uh, right? Okay. So this is right. So this is your gate voltage will nothing but the voltage drop across the oxide plus the voltage drop across the silicon, and the voltage drop across the silicon is always surface potential. Okay. So so means here you see there will be a change in the formulable between your gate and your silicon, because you have your silicon is at zero, because you see your anyway your formulables will be flat because there is no current flowing, right? Um, so this did so if you see the formulable, if you so this difference here, right? So this difference here, this will be QVG, right? So you are applying gate voltage. So as you go on increasing your gate voltage, you could also means you could think of, you could just, if you pull it down, everything will be pulled down, right? So basically your conduction means your oxide means you could think of, right? Because if you increase your gate voltage, your electric field will increase. If your electric field increases, the voltage drop across your oxide will increase, voltage drop across the silicon will also increase. Okay. So any questions here? Okay. So now, if you go to, we start with accumulation. So yesterday, so basically accumulation means when you're applying negative voltage at the gate, right? So for a NMOS transistor, if you apply negative voltage at the gate, right? So your holes will accumulate at the surface, right? And that condition we call the accumulation. So here, your if you see, um, again, if I go to, so here your Bg oxide and your silicon here, right? So here your Bg is negative, right? If your gate voltage is negative, this is your oxide, right? So, so there will be a voltage drop in the oxide, that is Vox, the oxide voltage drop, because the moment gate voltage is negative, you are applying some gate voltage, there will be electric field, right? But in this case, the electric field directions will be opposite. So from body to gate, right? So, so, so your holes will accumulate here, so your holes are accumulating at the surface. So if you look at the silicon, right? So if you look at the silicon, there is a net charge, right? Here the net charge is holes, right? Right. So you have a net charge. So there will be a voltage drop, right? So since silicon is not neutral anymore, silicon there is a net charge. So the voltage drop is there will be some voltage, and this voltage will be negative because you see, again, if you think of your Kirchhoff's voltage law, here I am applying negative voltage and here I have zero, right? And this voltage will also be negative, right? So if the voltage drop here is psi s, that is the sub, right? And this psi s will also be negative, right? So if the psi s is negative, right, your surface potential is negative, then your bands will bend up, right? So basically your bands bend up, right? Because um, uh, your conduction band ECX, right, will be EC in the flat band condition, and plus Q psi S. So your Q minus, so your charge is negative, right? So you could think of plus minus Q times minus uh, psi X, right? Minus psi X. So this will be ECFB plus Q times psi X, right? Right. So your bands will bend up, right? Your bands will bend up here. So you see here the bands are bending up, right? Right. So this condition is accumulation condition, and here there is no depletion region, right? So there is no depletion region, but these bands will only bend. So I have so basically this region is very small because holes will accumulate, right? And holes will accumulate at a very thin region. The holes will accumulate at the surface. So this is very small, right? This part is very small, right? The thickness, the accumulation region, thickness of the accumulation region is very small. Okay, so let's see, right? So if I'm talking about the charge in the silicon, right? So when I talk about charge in the silicon, so charge in the silicon is always the Q, the charge times your hole. So because your, if you look at x direction, so your charges, the concentration of charge is changing. So I could write down it as Q times Px plus nd plus, so the, minus nx um, minus na minus, right? So this is actually total charge in the silicon, right? This is total charge on the silicon. But if you see, the silicon is um, p-type doped, right? Your silicon is p-type doped, so there will not be any nd plus, right? So nd plus will not be there because since this is p-type dope, so we'll have only acceptor ions, right? We will not have any donor ions, right? Right. So you could um, write in this way, right? um, if I look at px, right, so this is so whole, I could write down this is ni exponential, right? uh, so I could write down this ex, right? So I know that p, the number of holes is nothing but ni exponential ei minus a by kt. right? But if I go in the x direction, right? So this is my x direction, right? So this is my x direction here, right? And when I have not drawn ei here, so ei will be something like this, right? Right. So ei will always be between ec and ev, right? So and if ec and ev are changing, then ei will change, but Fermi level will not change. Fermi level, uh, because you have your Fermi level will always be flat, because I am not applying any voltage to the body, right? So the Fermi level will always be flat because there is no current flow, right? um, in the x direction. So if you see, so this gap between ei and ef is increasing, right? If you at the surface this gap has increased, that means we have more number of holes, right? Holes accumulated. So so basically, if I want to write um, EIX minus EF, right? So EIX, see, EIX is nothing but EI in the flat band condition, plus I have added this Q psi X, right, minus EF, right? Right. So this is my this point, right? So this here, this is Q times psi X, right? Right. So EI is also bending up, right? Right. So I could write it like this. Right. So this is nothing but EI in the flat band condition minus EF plus Q times psi X. Right. So if I use that, right? So Ni here exponential EIFB minus EF plus Q psi X divided by KT, right? So I could write down this as EI flat band minus EF by KT exponential Q psi X by KT, right? So if you look at this part, right, this part here, so this is nothing but your Na, right? This is nothing but your doping, right? So your Na is nothing but Ni exponential Ei minus F by Kt. So your um, um, so your Px is nothing but exponential Q psi x by Kt. So here you see uh, your and at the surface, right? So the number of holes accumulating at the surface is nothing but exponential Q psi s by Kt, right? So please, it's basically here, your surface potential is negative, right? So in this case, right? So you could see also here, as you go on increasing your negative gate voltage, right? Your hole at the surface is also increasing exponentially, right? So this is a very important equation. We may use it later. So right. So if your surface potential is zero, number of holes at the surface is Na, right? So basically, if you see, if there is no band bending at the surface, right? If you're not applying any gate voltage, that means there is no band bending at the surface. So your surface potential is zero. So that means your holes is nothing but equal to Na, right? The doping in the substrate, right? But as you go on increasing your gate voltage, your psi s will increase, but psi s will increase in the negative direction. So your number of holes will also increase, right? Okay. Um, Okay, so this is accumulation. So if you apply negative voltage, your holes will accumulate at the surface, and this accumulation happens exponentially, right? Okay. The next is depletion. So depletion we have already discussed. So basically, your psi s is zero. I mean, sorry, your gate voltage. So in this case, your gate voltage is somewhere between 0 and threshold voltage, right? Your gate voltage is somewhere between 0 and threshold voltage. That means surface has not inverted properly. Um, so since you're applying positive gate voltage, your surface potential or your psi in the psi your psi is more than I mean it's positive. and since the psi is positive, your band will bend downwards, right? So your band will bend downwards, right? So you see your band is bending downwards, right? Your band is bending downwards. So here also I could draw EI. So EI is always at the middle. So you see uh, your EI will also bend downwards, right? So this is also your Q psi s, right? Right? Whatever band bending. So your band bending at the surface is always Q times psi s. So similarly here, you could also right, um, right, um, yeah, here I also forgot to tell you. So you see your total silicon charge, I have hole charge, electron charge, as well as your negatively charged exciton, right. But in the accumulation condition, your nx is very less, right? In the accumulation condition, your nx is very less, so your nothing but a q charge is nothing but px minus n minus, right? So this is means this is very less, right? So very less in the accumulation condition, because accumulation condition there is no electrons, right? um, right. So so your charge will always be p q times px minus na. So since your number of holes at the surface is increasing exponentially, so your total silicon charge is nothing but your whole charge. Okay. So in this case, right. So as I told you, right. So um, um, you could write the charge. Um, So in the depletion case, your silicon charge, mean silicon charge, I could always write this as Px minus Nx minus Na minus, right? So this is the charge neutrality condition, because total charge, so if in the when I'm not applying any gate voltage, so this should be zero, right? Um, so if you see, so in the depletion condition, if you look at the region, depletion region, if you look at the depletion region, right? So your px, right? You see the whole, because your um okay, I could write down this one like this. So your px is nothing but ni exponential eix minus ef by kt, right? But you see here ei is bending downwards and your ef is flat and ei is bending downwards. So the distance, the energy difference between ei and ef is will reduce, right? So eix minus f will reduce with increase in gate voltage, right? With increase in gate voltage, right? So as you go on increasing gate voltage, your band is bending down, right? Since the band is bending down, so EI and EF is reducing, and also if you go on increasing VG, and your EI X minus EF will be negative. This will be negative also, right? So that means the number of holes. So this mathematical explains, right? The number of holes at the surface will reduce, right? Number of holes will reduce, right? Because EIX minus EF will become negative. That means your PX will reduce, right? But your NX, right? Your number of electrons is nothing but Ni times exponential um, F minus EIX by KT, right? So your uh, EI minus EF is reducing, right? And EF minus EI is also, right? EF minus, you see, EF minus EI was negative, right? So when there is no, when we're not applying any gate voltage, EF minus EI was negative, right? So in the beginning, EF minus EI in the beginning, when VG 0 condition, your EF minus EIX was negative, right? Right. If you increase VG, so EF minus EI will be positive, right? So it will slowly become positive because you see your EI is going below F, right? So it explains that the number of electrons is increasing. So we also explained that, we also discussed the physics, right? So as you go on increasing your gate voltage, you will have more depletion charge, right? So your depletion charge, um, your depletion charge is increasing, so your surface, your potential is increasing. So your potential increasing means your both the junctions are far biased, and we have electrons injected from source and drain to the channel, right? Source and drain to the body, and they're collected at the surface side. So this also mathematically explains, because as you go on increasing your surface potential, your EF minus EI becoming positive. That means your NX, your number of electrons is increasing, right? But in the depletion condition, when I talk about depletion condition, your NX. So you see, what is the charge, right? So if I look, um, if I see in the depletion regions, I have N plus here, and I have my negatively charged acceptance here, right? Right? And the total depletion charge is nothing but how much is the total depletion charge? So Q times Na times WD, right? So the this is the depletion width, right? Q times Na times WD. This is the total charge per centimeter square, right? So unit is per centimeter square, right? And I'll at the same time I have Nx, right? So number of electrons also increasing. So total number of electrons, so is nothing but, uh, you see at the surface, it will be, it means I could do some math here. Let me see, right? So, okay, let me take that, right? So, your EF minus EIX, I could write down, because your EIX is nothing but EF minus, so EIX nothing but whatever in the flat band minus Q times psi x, right? So this is EF minus EI flat band uh, plus Q times psi x. So your NX will be Ni exponential EF minus EIFB divided by KT times exponential Q psi x by KT. Right. So so this part is, this is nothing but Ni square by Na, right? Exponential uh, Q psi x by KT. Right. So this is the total number of electrons, right? So basically, if you want to find the total number of electrons n, then you have to 0 to x direction, you have to integrate, right? Right. You could integrate, that is from 0 to WD, right? So that you could do, right? But at the surface, so if you want to find the number of electrons at the surface, because electrons will accumulate at the surface only, right? So you see, this is nothing but Ni square by Na exponential Q psi s by KT, right? So in the beginning, so we have very less number of electrons. If you look at this number, Ni square by Na, when psi s is 0, right? When there is no gate voltage, I have Ni square by Na number of electrons. Now this number of electrons is increasing exponentially, right? As you go on increasing gate voltage, right? But in the depletion condition, the total number of electrons is less than in the depletion condition. The total number of electrons, see, this is the important point. In the total number of electrons is less than Q Na times WD, right? So because the total charge, you see, the total silicon charge, is nothing but your q times whole minus n minus na minus, right? Right. So anyway, so in the depletion condition, when we're looking at the surface, right? When we're looking at the surface, we do not have any holes. Holes are repelled. So I could write down this as minus q times n plus na minus. So total charge is nothing but because of electrons as well as your negatively charged acceptor ions, right? But in the depletion condition, your n is less than na minus, right? In depletion, this is in depletion condition, right? So that's why you do not have a sufficient number of electrons. Your gate voltage is not enough that you have not your Na is less than like if Na is 10 to 17, let's say you have doped 10 to 17, so Na is much less, right? Na is less than 10 to 17, right? So this is the depletion condition. So in the depletion condition, right? So please keep in mind, in the depletion condition, uh, you have some electrons in the channel, right? You have some electrons in the channel, right? Or you have some electrons in this region, right? So you have some electrons in this region, but these electrons are not very high, right? So it's not very high. So you cannot, means if it is very high, then it will be inversion, right? But these electrons are not very high. And another thing, right? So with Vg, your gate voltage, right? Your uh, electric field, right? So electric field in the silicon, right? Electric field increases with gate voltage, right? So since this is a very less gate voltage, it's a positive gate voltage, but less gate voltage, the electric field is low, right? Electric field is not very high. Since the electric field is not very high, even if we have the electrons have been injected to the sub body, because these junctions are formed by electrons have been injected, but they are less in number. But also, since the electric field is high, these electrons are not, all the electrons are not at the surface, because they are not, means the field is not very high to pull them to the surface, right? So to make the story short, so I have in the depletion region, I have depletion condition, I have my depletion charges, right? I have some electrons, because I have some electrons that are coming from both the junctions. But these electrons, and I have field, but this field is not very high. So the electrons, all the electrons are not pulled to the surface, right? So basically the channel has not formed, right? For the channel formation, the electrons, they're injected, but they're collected, right? So they're injected and they go to the surface because the field is very high. The field is not very high, so the electrons are distributed, right? So you could think of these electrons are distributed, the electrons are not right at the surface because the field is not very high to pull them to the surface, right? Okay, and these electrons, the density of electrons are not high as the total number of depletion charges, right? So that's why condition is depletion condition, right? Okay, so this is the depletion condition, but you could see the number of electrons increase exponentially with psi s, right? Increase exponentially with with psi s, right? Okay, so now if you go on increasing the gate voltage, right, at some point, right, because your we saw that the number of electrons at the surface is nothing but ni square by na times e to the power q psi s by kt, right? But at some surface potential, your number of electrons will become the number of holes, earlier holes present, right? Na, right? Because I'm depletion, I was telling that number of electrons is less than Na, right? But at some point, the number of electrons will exceed the depletion charge, right? Right? And that will happen. This is the border, right? Where the Ns will become Na, right? And if I do that, then your psi s, right, is Kt by Q ln Na square by Ni square, right? Right? And that psi s means, if you see what is this one, this is nothing but 2 by Kt by Q ln Na by Na, right? So 2 Kt by Q ln, so this is nothing but 2 times psi b. What is psi b? Psi b is the right. So psi b. So if you see in the flat band condition, if I draw the band diagram, so I have EC EV in the flat band condition, right? So this is my EF because this is a p-type silicon, right? And I have my EI somewhere in between, right? And this I call the psi b, right? So this is the distance between, I mean, energy difference between EI and EF, right? 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 So, and we know that this psi b is KT by Q ln Na by Ni before, right? But here, for the inversion to happen, your surface potential should be equal to 2 psi b, right? When the surface potential becomes 2 psi b, then the number of electrons at the surface becomes equal to Na, and we call it inversion condition, right? So what does it mean? So if you look at the band diagram, I have my EI here. I have my EI here, right? So this is my psi b, right? And your EI goes below below EF by another psi b, right? So the total band bending here, total band bending is two times psi b, right? So when the surface potential becomes 2 times psi b, that means we have enough number of electrons, right? So that this number of electrons is equal to the number of holes at the surface in the flat band condition, right? So this the condition for inversion is psi s equal to 2 psi b, and psi b is nothing but 2 kt by q ln Na times Ni, right? Right. So basically, whenever your surface potential reaches this factor 2 kt by q ln Na by Ni, this condition we call the inversion condition, right? So to summarize, if your psi s is less than 0, this is my accumulation condition, right? Your surface potential less than 0. Your psi s is somewhere between 0 and 2 psi b, so that is my depletion, right? And your psi s is more than 2 psi b, so this is your inversion condition, right? And if your psi s equal to 0, right, so this is your flat band, right? Bands are flat, so this is the flat band condition, right? Right, so these are the 4 conditions. So I have accumulation, so when your surface potential is less than 0, depletion, when the surface potential is somewhere between 0 and 2 psi b, and psi b is nothing but kt by q ln Na by Ni. So psi b depends on the doping of the p-type substrate, right? And inversion is when your psi s is more than 2 psi b, right? And flat band condition, when psi s is 0, there is no charges in the silicon, no potential, right? So when psi s equal to 0, that is your flat band condition, right? So these are the 4 important things. If you understand this, then we could go ahead, right? So any questions here? So everybody understood? Yeah, answer, right? Yes or no?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, fine. All right. So okay. So basically, okay. So here, I have 12 minutes. So basically here, um, so your surface potential um, can be more than 2 psi b, right? So if you go to more than 2 psi b, so your means it is inversion, then you'll go to strong inversion, right? Strong inversion means you have number of electrons at the surface is much higher than the initial doping of the substrate, right? Right. Okay. So let's see, right? So here basically let's look at the, so as I told you, right, your total charge in the silicon, right, total charge in the silicon, right, is equal to uh, the depletion charge. I'll tell depletion charge and the inversion charge, right. So what is the depletion charge? So basically if I see now I mean I am talking about when your gate voltage is positive, your VG is positive, VG positive. So I have depletion charges here. I have depletion charges, and I have also electrons, and if the and I have electrons which is accumulated at the surface, right? So this is I have a channel region, right? So total charge in the silicon is nothing. If the depletion charge, depletion charge is how much negatively charged acceptor ions are there plus Qi, right? So please keep in mind. So when you talk about charge in the silicon, we always talk about per centimeter square, right? So because when you look at the surface, right? So I mean, so when you look basically, why? Okay, so if you look at the layout of a transistor, right? So if I look at a layout of transistor, so this is the effective area of the transistor, right? This is the active region, right? So W times Lg, right? So this is my width, and this is Lg, right? So so in the MOS transistor means terminology, so we tell charge, always charge is unit of charge is charge per centimeter square, the centimeter square of the area, right? So if you want to find the total charge, I could multiply by the W times Lg. Similarly, the capacitance, when you talk about capacitance, this is capacitance per unit area, right? Okay, so this QD, um this um QD is nothing but Q times Na times WD, right? Right. So then this becomes, this is per centimeter cube. So if you look at the unit, this is per centimeter cube, and this is centimeter. So this will be per centimeter square, right? Similarly, when I talk about Qi, right? So I have uh, Q. I have means mostly the electrons are at the surface, right? Electrons are at the surface, but there is a finite. I mean, basically, if you see, uh, right? So the electrons are mostly accumulated at the surface, right? So and I have this thickness, right? This is called the inversion thickness, right? So this is very small because the electrons are means Ti, the inversion thickness, the inversion charge thickness is very small. Inversion charge is nothing but the mobile charge, my electrons, right? And their means your field is very high, the all the electrons are at the surface, and this thickness, this inversion thickness is always very low, right? But if I want to find a charge per centimeter square, I have to multiply by the inversion thickness, right? QNSTI, right? Okay. Uh, so so when you are increasing your gate voltage, right? So when you are increasing your gate voltage, your depletion charge is increasing, your inversion charge is also increasing, right? Right. Okay, so let's look at my inversion charge. Inversion charge is Q Na times WD, right? And WD, I had when we derived the WD yesterday. Um, so let me find out if I have somewhere. Um, yeah, your WD is if you look at your notes yesterday. So this is 2 epsilon Si psi s divided by QNA, right? So this is nothing but 2 epsilon Si QNA root over psi s, right? Right. So means so we can go to, we did it yesterday, right? So you see here, yeah. So here we have derived, right? Your psi s equal to QNA divided 2 epsilon WD square. From here I could get WD is nothing but 2 SI 2 epsilon QNA times psi s, right? So so here you see this part. If you look at this part, this is a constant because your epsilon is constant, Q is constant, EONA doping, you have already doped it, so doping is constant. So this is some constant, let's say K1 times root over psi s, right? So I could try that your depletion charge is proportional to root over psi s, right? Your depletion charge is proportional to root over psi s. Okay, so my inversion charge, right? Inversion charge basically inversion your Qi is as I told you, this is Q times Ns times Ti, right? So your because yeah, you see the your inversion because basically your electrons are accumulated at the surface. So these QTi parts are almost constant because anyway this inversion thickness, we have some inversion thickness and the inversion thickness is very small. But this Ns, as we derived here, right? So this is Ni square, Ni square divided by Na exponential times Q psi s by Kt, right? So if you see your inversion charge is proportional to Kt, right? So I could write down this as K2 times e to the power K3 means Q psi s by Kt, right? Right. Okay. So if you see your depletion charge is increasing root over psi s, right? So see your Vg when you go if you increase your gate voltage, your psi s is increasing, your surface potential increasing, but your depletion charge is increasing root over psi s, but your inversion charge is increasing exponential psi s, right? So if I plot, if I see, if I somehow plot here the total silicon charge, right? So my QD is increasing root over psi s. That means if my this is my psi s, so then I will have something like this, right? This is root over psi s, right? Right. Okay. And your QI, so this is my QD, and your QI is increasing exponentially. So if I do so, you see, this is a linear plot, so this is increasing exponentially. So means I have to go, right? So this Qi, right? So basically your Qi will drop, and this point here where the Qi becomes more than Qd, this is almost equal to 2 times psi b, right? Right? And if I plot the silicon charge is the summation of both of these, right? And it will be something like this, right? So if you could add Qd and Qi, so your silicon charge will be sometime will be somewhere like this, right? 12 marks, right? So so this is my depletion condition, right? So when I'm talking about the depletion condition, so this is my depletion region. So where, right? And and this is inversion. So your inversion charge is more than the depletion charge, but the one point is in the depletion region, even if you do not have much inversion charge, you do not have more electrons, but your depletion charge is increasing exponentially, with root over psi s, right? It's a limited increase, right? Root over psi s. But the moment your transistor inverts, right, your inversion charge is increasing exponentially, right? And so what happens? So basically, if you look at theoretically, so your gate voltage is Vx times psi s, right? So this is my Kirchhoff's voltage law, right? KVL, right? So whatever gate voltage you're applying, so your gate voltage is nothing but the drop in the oxide and the drop in the silicon, right? And the drop in the silicon is psi s, and drop in the oxide is Vx, right? And we had done so I could if there is an electric field, so Eox times Tox plus is um, and so I know the displacement vectors because This is my oxide. This is my oxide. This is my silicon, and I have electric field, right? So electric field, this is electric field in the oxide, this is electric field in the silicon. Please keep in mind, so electric field in the oxide will be different from the electric field in the silicon because the change in epsilons, right? So there is a flux, right? So the moment I give some gate voltage, there are positive charges, right? So that means there is a flux coming from gate towards substrate, but that flux density displacement vector is d. So d, we know that Gauss law, right? It means we know that d is epsilon times electric field, right? So epsilon times, so at this interface, right? So if you look at this interface here, if you look at this interface here, so Eox times field in the oxide is nothing but epsilon Si field in the Si, right? But the but if you look at the, see, if you look at the flux line, this is nothing but right, um, right. So this part here, right. So this part is nothing but your charge in the silicon, right. So this, if you go by the Gauss law, right. So your del dot D equal to rho, right. So basically, you see, your Gauss law tells you that del dot D equal to rho. So in this case, dd by dx equal to rho. So dd is dE by dx epsilon equal to rho, right? So dE by dx equal to rho by E, right? So rho is, if rho is the charge in the silicon, and this is in the silicon, so the electric field means your dE is nothing but rho silicon divided by epsilon silicon dx, right? So if you integrate, so if you integrate here, right? So the total charge is nothing but your electric field. I mean, basically you have, so if you integrate this, this will be your total electric field entering silicon, right? So this will be your epsilon Ci, means the electric field in the silicon, and so and this here you could write down if electric field in the silicon is nothing or epsilon in silicon, so you could rho dx, right? So 0 to x, right? And this part is nothing but the total charge in the silicon, right? So this is the total charge in the silicon. So here I could also write down this as your Eox means electric field times your oxide thickness. I could write down is QSI divided by epsilon ox, right, times Eox plus is, right? So if I go from here to here, so this is nothing but Q silicon divided by Cox because plus is, right? So my gate voltage, I could write down the psi s plus Q Si plus Cox, right? So so your gate voltage, whatever gate voltage I'm applying, so this is Q, means whatever charge in the silicon. See this, the voltage drop. This is the voltage drop in the oxide, right? So voltage drop in the oxide depends on the electric field in the oxide, and electric field in the oxide depends on the charge in the silicon, right? So that's the reason your Vox here, your Vox, right? So this is your Vox part, right? Depends on the charge in the silicon, right? So you could also write down is Qd by Cox. This is the depletion charge plus Qi divided by Cox plus Is, right? Okay. So what I'm telling here is, you see, this both of this is the voltage drop in the oxide, right? So if you look at the charge plot, right, your silicon charge after inversion, your silicon charge is exponentially increasing, right? After inversion, your silicon charge is exponentially increasing. That means if you plot your oxide, I mean voltage drop across oxide, right? If I plot the voltage drop as a function of psi s, right? So your voltage drop was increasing. Let's say, means you could plot it. I mean, your voltage drop is increasing with psi s, right? Because you're electrically increasing. But after inversion, suddenly it will increase, right? Very high, right? Because you see, because your inversion charge is increasing exponentially, so the voltage drop will increase exponentially, right? Right? And this is not, this happens at 2 psi b, right? So what happens is, since your voltage so basically after you increase, after inversion, your voltage drop increases exponentially, or voltage drop increases drastically. So there is no change in the so after inversion, so I could write down after inversion. So the gate voltage, most of the gate voltage drops across oxide, right? Right. So since most of the, so and the potential, the drop in the silicon, drop in silicon, which is your psi s, drop in silicon, which is psi s, saturates, because if for applying any gate voltage, so there is a lot of increase in charge. So your most of the gate voltage drop across your Viox, your means your oxide. So there is less voltage drop in the silicon. So that's the reason. If you plot, I will discuss this later also. So if you plot your surface potential as a function of gate voltage, right? If you plot your surface potential as a function of gate voltage, let's say this region is depletion. So in the depletion, your surface potential will increase, right? But the moment it invert, your surface potential will saturate, right? This is what this is how uh, your this is how your surface potential is drop in the silicon. So this surface potential is nothing but your drop in silicon, right, with Vg, right? So it increases, then after inversion it saturates, right? So the moment your transistor inverts, right, so most of the voltage drop across oxide, right? So that's the reason. So once the transistor inverts, you don't want to go more than that voltage, very high voltage, because your drop across the, because after inversion most of the voltage drop across the oxide. So if you go to higher gate voltage, then the field across the oxide will be very high, right? Your voltage drop across, because the oxide thickness is same, but the drop across the oxide is increasing. So the field will increase and your device will break, right? So that's why you do not go, means so basically this is your threshold voltage, right? So where the inversion happens, this is your threshold voltage. So you do not go means your um, means you do not go very high voltage, you get voltage much higher than threshold voltage, right? If you go to very, because if you go to very high get, means get voltage higher than the threshold voltage, very, means higher than the threshold voltage, then the field across the oxide is increasing and your device will break sometime. Okay, so this concept, so means we'll slowly understand. So means I'll stop here because already we have 8 minutes um, past 12. So I'll stop here, and but if you have any questions,